Hello everyone and welcome to Unit 3 of the ROS Navigation course. In this unit we are going to talk about robot localization. So, in previous unit you have already seen how important is localization. Yes? So, when you have a map, when you have built a map of your environment, it is mandatory, your robot needs to know what position and what orientation has the robot in each moment within that map. Yes? So this is very important because if you cannot know that, the map is completely useless. So this is, like I say many times, this is like going to a new city and buying a map of that city. But if you don't know where you are within that map is completely useless. Yes? So this basically is the robot localization. Okay, so to start with this unit, let's do like we did in the mapping unit. Let's have a look at Rviz and what elements we need to take into account in Rviz when we want to perform robot localization. So for that, we are going to start with this exercise, with this example guided exercise. Yeah. So the first thing is to execute this command here. There we are, which will launch an AMCL node. Yes, this is a demo. Excellent. And we are going to launch Rviz as well. Let's do it here. And let's open the graphical tools by hitting this button here. There we are. So now Rviz will appear here. Here we can see it. Okay, we have the configuration from previous unit, so let's remove, well, we can leave these, in fact, yes, because we will need them. So when working with localization in Rviz, we basically need to check three displays. One is the laser scan display, the map display, and the pose array display. Yes, these two you already see, so how to visualize them in the mapping unit. Yes, here anyways we will need to configure it because, as you can see, the laser is not showing because the topic is wrong. Yeah, this is the topic from the Kabuki simulation. So the topic in this simulation where the laser data is stored is the scan topic. There we have it. So now we can visualize the laser data. And the map, we are visualizing it correctly. So no problem here, yes? The map, it is still the same topic, map topic. So now, in order to visualize localization, we will need to add the pose array display, which you can find it here. Here it is, pose array. Yes? Then here you will need to configure the topic, as always. In this case, the topic is point cloud. A particle cloud. Sorry, here you have it, yes? So this is the topic you need to add here in the pose array, okay? So by adding this, I can visualize these characteristic arrows that are used in order to visualize localization, yes? Then, let's continue with the demonstration. Yeah, here we are. Okay. So, what we are going to do now is basically two things. First of all, we are going to use the 2D pose estimate tool, yes, in order to tell Rviz where our robot is. Yeah. So let's have a look at the simulation to guess more or less where it is within the map. Okay. The position and the orientation. Yes. Well, I think more or less we can say it is more or less, yes. It is here. Yeah. So let's put it. Let's place our robot there. There we are. Yeah, it's not very accurate, but well, this will be fixed when we move the robot. Yeah, yeah. Probably it's as you can see, the orientation is much more down Well, let's fix it a little bit. Here, we'll place it that way. Okay, a little bit better, yeah? So now what we will do is to move the robot around. Yes, we are going to use the keyboard teleop program in order to move our robot using the keyboard. So let's launch this keyboard teleop launch file here. And let's begin to move a little bit the robot around the environment. There we are. So I am moving it using the keyboard. Yes, the different keys. There we are. Let's see how it is progressing here in Rviz. Okay, so yeah, the lasers more or less match the map, so it is quite accurate. And as you can see, if we take out for a moment the robot model, you will see that the arrows have concentrated also in one zone. Yes, they are not dispersed as they were at the beginning. Yes, so this is similar to the demonstration you did in the basic concepts unit. But now let's see what really is happening behind all this. Yeah, so let's have a look at what is going on there. So basically, we are using here the Monte Carlo localization. Yes? So this Monte Carlo localization, also known as AMCL, it is an algorithm used in order to solve the localization problem in robotics. Yes? And basically what this algorithm does is to create random poses. Yes? Now they are quite concrete. Oh, sorry. Let me take out this. Yes. So it generates guesses, possible poses where the robot is or where the robot is going to be. Yes. Let me find these arrows. Yeah, there they are. Yes. So each one of these arrows, it is a possible position of the robot. Yes. Then depending on the readings of the environment that the robot does, in this case using the laser, depending on this reading, it discards the guesses that are wrong and it concentrates more guesses in the more probable good positions. Yes, so that's why at the beginning you have all the particles dispersed, yes, like this, like here. Yeah, you have all the particles dispersed, yeah? But at the end, the particles are much more concentrated in one point, yes? Because while new data is being registered about the environment, all the wrong guesses that this algorithm does at the beginning are discarded. Yes? Then, this Monte Carlo localization algorithm is used in the AMCL package of ROS. Yes? This package provides the AMCL node, which uses this Monte Carlo localization system in order to localize the robot in an environment. Yes? So basically what this node does is to subscribe to the data of the laser, the data of the map of the environment, and the transformations of the robot, and with all this data, it publishes an estimated position in the map of the robot. Yes? So basically, what has just happened in this example, in this demo, is, first of all, you have launched a AMCL node. Yes, in this launch file, here, the command you executed here you are starting an AMCL node, a pre-configured AMCL node. Yes? Then we set up a position of the robot, an initial position of the robot. in order to help the system localize the robot at the beginning. Yes, although at the beginning it is it's not accurate at all. Yeah, the arrows are very dispersed. Yeah, the possible guesses of the position of the robot are very different. Yes, then what happens? Well, when you start moving the robot, in our case we moved the robot using the keyboard teleop. Yeah, when we started moving the robot around the environment, the robot kept getting laser data. Yes, and it is also subscribed to the map topic, which is map, and to the transform topic, which is TF. Yes, then with the data from the TF topic, the data from the map, and the readings from the laser, with all this information, the AMCL node publishes an estimated pose of the robot. Yes, and it uses these two topics in order to tell this information: the AMCL pose and the particle cloud topic. This particle cloud topic is the topic that we are visualizing here in these arrows. Yeah, so this particle cloud topic is the topic that allows us to visualize this localization. Yes, so basically that's it. Yes, the AMCL node gets data from the laser, from the map, and from the transforms of the robot, and provides an estimated pose of the robot. And all of this is done using the Monte Carlo localization algorithm, which is also known as the particle filter localization. Yes? So this is basically what is going on here in this example in localization. Yeah, this is in general terms how it works. Okay? Now, let's do a very quick flashback here. So when I started Rviz, I was able to visualize the full map. Yes? So how do you think I am getting this map? Do you have any guess? Why I'm able to visualize a full map if I haven't done any mapping at all? Yeah, so that's it. That's because I am providing this map. So if you remember from the previous unit, we used the map server node in order to provide a map like this. Yes, so this is basically what I am doing here. Yes, if I have a look at this AMCL demo.launch file, let's have a look. A moment. ROS Husky navigation package. Here I can see the AMCL demo launch file. So there we are. Yeah. So inside this launch file, I can see that I am launching an AMCL launch here, also a move base. Yeah, but this don't worry about this one for the moment. I am launching here the AMCL node, and here what I am doing is to call this map server node, and I am providing a map file here as an argument. Yes, in this case the map which I am providing is here in the Husky navigation package in the maps directory. Yeah, so it is, let's clear this, it is here. Yeah, this is the map that I am providing to the AMCL node. Yeah, so that's the reason why I am able to visualize the map. Yes, because I previously have already created a map, I have saved that map, so now I am able to provide it. Yes, remember you saw this in the previous unit. Okay, excellent. So yeah, I will let you now some time to do an interesting exercise, which is to launch the system with a different map, with a map that is not this one. Yes? So let's store all of this we have here. Let's just stop it. There we are. Yeah? So what does this exercise require? First of all, have a look at the AMCL demo launch file. This is the file that we have just visualized. Yes? You will see that what it's actually doing is calling another launch file, amcl.launch. Yeah? Remember? Let's see this again. Yes? So this launch file, what it's really doing here it is calling another launch file, which is the real launch file that starts the AMCL node. Yes? Then create a new package named my AMCL launcher. Okay, similar to this one. So you create another one, which is my AMCL launcher. Inside this package, create a new directory named launch. Okay, since it is the first exercise, I will do this as well with you. So create a new package called my AMCL launcher. There we are. Then inside this package, create a directory named launch. There we are. New directory named launch. And then inside of this directory, create a new file named changemap.launch. Okay, so I will create a new file named changemap.launch. There we are. Excellent. Then copy the contents of the AMCL launch file into this new file. So let's go back to the ASCII navigation package, to the launch directory. Okay, so here I have the AMCL launch. Yeah, so I'm going to copy this to my workspace. Yeah, so it will appear here. Here it is, yeah? So now I will copy the contents of this file and I will pass them to my changemap.launch file. Yes? There we are. So now I can delete this AMCL and I have my changemap.launch file with all the parameters required for AMCL, which we are going to analyze later. Yes? Then inside this launch file, modify the section where you launch the map server node and provide a different map file. So here, what you will have to do in this case is to copy this line here, yeah, this section here, where you load the map. Yes, you will copy this section here. There we are. Okay, now with this section you will have to modify the map that you will load. Yes, so here I'm loading this mymap.elm file, so you will have to load a different map. Yeah, so for instance, here in the maps directory you can see that there are other maps you can load. Yes, so you will have to modify this in order to load another map. Okay, then as a result you will see something like this. Yeah, the robot with the localization system and another map. Yes, you are not seeing anymore the cafeteria map. Yes, but this is because you are loading a different map. Yeah, excellent. So yeah, let's continue. Okay, yeah, so here you have exercise 1.4. In exercise 1.4, what you will have to do is to get the pose of the robot without using this particle cloud topic, which is represented by the arrows, yes? So if you remember from my previous explanation, I said that the AMCL node publishes the estimated pose in two topics. One is the AMCL pose and the other one is the particle cloud topic. Yes? So the AMCL node writes in these two topics. So until now we have been working with this particle cloud topic, which is represented by the arrows in Rviz. Yes? But now, here in exercise 4, I want you to get information about the estimated pose by using other methods. Yes, I will say like this, by using other methods, without using the particle cloud topic. Okay? Excellent. Excellent. So then, after this, you have another exercise, yeah? So you will have some work to do here. So the exercise 1.5, it's create a service server that, when called, returns the pose, position and orientation of the robot at that exact moment. Yes? So you have to create a service server that you can call, and this service server will respond with providing the estimated pose of the robot in that moment, in the moment that you perform the call to the service, obviously. Yes? Then you will have to get this pose here in front of the fridge, and also here, which is in front of the door, yeah, in front of this door here. So here and here in front of the fridge. Yes? You will have to create this service server in order to know the pose of the robot, position and orientation in these two spots. Okay? Great. So yeah, do these exercises. You can pause the video whenever you want, as always, and I will continue with the explanation. So the next thing we are going to have a look is to the hardware requirements. Yes, we are always seeing this. If you remember from the mapping unit, we had to provide a good laser data and a good odometry data. Yes, besides the transforms, which we will see later, yes? But we need, in order for AMCL to work properly, we need to provide a good laser data and a good odometry data of the robot. And we have to add a good map data, of course. Yes? So we need to provide a good map data. Because if the map is wrong, is not properly done, the localization will be also wrong. Wouldn't make any sense, in fact. Yes? So we need these three things. Provide good laser data, provide a good odometry data, and provide a good laser-based, because it's built using the laser, map data. Okay? Then here you have a very simple exercise in order to check the different topics where the laser, odometry, and map data are published. You can do it as well, of course. Then let's have a look at the transforms. As we saw in the previous unit, mapping transforms are very important. Yes? And I hope you got a general idea of what transforms are. Yes? If not, I want to remember you that in the Ignite Academy you have the TF101 course. You can take anytime. Yeah, you can start it whenever you want. Okay? This is a course dedicated exclusively to transforms. Okay? Then, for AMCL, what transforms do I need? I need two. I need the transform from the laser frame to the odometry frame. Yes? So this means that there must be a path through the transform tree from the frame of the laser to the frame of odometry. Yes? If you remember from previous unit, the transform tree, it is this here. Yeah? So this means that we need to make sure that we have a path from, let's get closer here, Yeah, so we need to have a path from the odom frame, which is here, to the laser frame, which is, let me check. Okay, let's minimize this. Yeah, here it is. The laser. Yeah, so we have a path from the laser, following all these arrows, to the odom frame. Yes? So, you can check in this exercise, this transform tree. Yes? So, yes, we need this path between the odometry frame and the laser frame. Yes? And also, the AMCL node looks for the transform between the laser and the base of the robot. Okay? And latches this transform forever. So this means that AMCL, the AMCL node, cannot handle a laser that moves with respect to the base. So the laser has to be fixed to the robot. Yes? This laser cannot be moving around the robot. Yes? Because if the laser moves around the robot, the transform wouldn't be valid anymore. Yeah, this is obvious. So yeah, in terms of transforms, you need to take these two aspects into account. Okay? Excellent. So yeah, let's continue. So now we are going to see how to create our own launch file for the AMCL node. Yes? In the mapping unit, if you remember, you did the same. So now we are going to do this for the AMCL node. So, as for the mapping, for launching an AMCL node, what you need to do basically is to create a launch file and specify, modify, or set the different parameters. Yes? These parameters here. Yes? So basically here you have a launch file that is launching the AMCL node. Yes? This is basically it. So we are providing a map because we need it, and then we are launching here the AMCL node. Yes? And we are configuring all the different parameters. Yes? So let's have a look at these parameters, some of them, the most important ones. Yes? There are lots of parameters. You can have a deep look in all of them, yes, but I'm going to do just a general overview, yes, because if not, this video will last forever. So let's divide as well the parameters in general parameters. Yes, so here, for instance, you have a parameter in order to define the odometry type. Yes, in this case it's diff, because odometry is from a differential drive. Yes, but you have different values. Diff, omni for omnidirectional, diff corrected. Yes, there are many. Usually you will use the differential drive or the omnidirectional. Yes, by default this parameter uses the diff value because it's the most common case. Okay, then here in general parameters you have also the different frames for the odometry, for the base of the robot, and for the map. Yes, which are odom, baselink, and map by default. And also here you have a parameter to indicate if your AMCL node will get the map data from the topic or from a service. Yes, this maybe you remember from the previous unit that when you provide a map, you can access that map by reading into the map and map metadata topics, or you can perform a call to a service which was called static map that also provides the map to you. Yes. So here you can decide if you want to get the map from the topics or from the service. Yes. For instance, then we have other parameters which are related to the filter of the algorithm. Yes. So are related to the Monte Carlo localization algorithm filter. Yeah. So for instance, here you can set the minimum or maximum number of particles. Yes, this is the number of arrows that you will see in Rviz in this case. Yes. So for instance, if you put this value, the maximum particles, you set this value to 3, for instance, you will always have these 3 arrows. Yes, you will have very few arrows, which obviously will decrease the quality of the localization. Yes. So, for instance, yeah, with these min particles and max particle parameters, you can regulate, you can configure the number of guesses you want your filter to do. Yes? Okay, yeah, you have some errors here related to the algorithm. Yes, I'm not going to get into this because this is more a mathematical issue. Yes, you can usually these values you can leave them to default. If not, you can try to modify them, whatever you want. Yes, but these parameters are related to the filter, to the Monte Carlo filter. Okay. Then here you have, for instance, yeah, here you have an exercise where you modify the min particles and max particle parameters. You set the min particles to 1 and the max particles to 5. So this means that the maximum number of arrows you will see, the maximum number of guesses that the Monte Carlo algorithm will do will be 5. Yes? So this will decrease a lot the quality of the localization. Yes? Obviously. Well, so you can try this exercise if you want. Then here you have some more parameters, which are in this laser parameters group. So for instance, you can set as well the minimum and maximum range for the laser, the maximum beams that your laser will have. You can configure different things about the laser. Yes? You have also here an exercise in order to test this laser max range parameter as well. And finally, once you have analyzed the different parameters, laser parameters, filter parameters, and general parameters, by modifying them directly in the launch file, so here, you can modify them directly here in the launch file. So finally, you will have to do another exercise in order to separate the parameters from the launch file. Yes, you also saw how to do this for the mapping unit. So you will have to create a YALM file that will contain all these parameters, and then you will load these parameters inside this launch file. Yes, so you will have, yeah, here you have the solution. You will have something like this. You will have a much more cleaner launch file and all the parameters in a separate YALM file. Okay, then finally let's have a look at the AMCL through services. So basically the AMCL node provides one service, which is this global localization service. And what does this service do? What this service do is to initiate a global localization, which means that all the particles will be dispersed randomly through all the free space of the map. Yes, we'll see an example of this now. But this is very interesting. Yeah? So the AMCL node provides this global localization service in order to disperse the particles, yeah, randomly throughout all the free space in the environment. And the AMCL node uses or calls one service, can call one service, yes, because you can configure it so it doesn't call this service, but you have the possibility to call to this static map service in order to get the map. Yes, you can also get it through topics, yes, but one of the methods is to get it using this static map service. So yeah, basically the AMCL node provides us one service, which is this global localization, and uses one service, which is this static map service, in order to get them up. Okay? Okay, then here you have an exercise in order to test this global localization service, but before that I want to show you more or less how this works, yes? So, yeah, let's run Rviz in order to visualize the particles. And there we are, so let's add again the pose array. Here we have it. Let's set the topic to particle cloud. Excellent. So now I'm going to relocalize. Well, in fact, it's okay. Yeah, the robot is more or less here, so it is accurate with a map. Okay. So now, as you can see, the localization is quite good. Yes. The particles are very concentrated in one zone, which means that the localization is good at this point. Yes? So what will happen now if I perform a call to the global localization service? Let's see what happens. So I'm going to do a call, ROS service call to the global localization service, which uses an empty message. Yes? This means that this service uses an empty message. So now if I remember, yeah, we have the particles very concentrated here in one point. Yes? So what happens if I execute this call to the service? Let's see. Okay. There we are. So this is what happens. All the particles are dispersed randomly through all the free space in the map. Yes? So now, obviously, if you want to localize your robot, you will need to move your robot all around their environment in order to discard, in order to keep getting data from the environment using the laser and keep discarding the wrong guesses. Yes? So this is what the global localization service does. Yes? And here you have an exercise where you have to create a file which will contain a service client. Yes, and this service client will perform a call to this global localization service. So here I have called the service by using this ROS service call command, and here you have to create a service client in order to call this service. Yes? And finally, we have a very interesting exercise to finalize this unit, which is this one here. Yeah? So let's read it, and then I will leave you so you can complete it. So inside the package that you created in the exercise above, yes, in this exercise here, we create a new file named squaremove.py. Okay? Then this squaremove.py, this Python script, will make the robot move performing a square movement. Yes? Then, when the robot finishes this square movement, it has to print the covariance of the filter. Okay, so what is the covariance of the filter? Okay, the covariance of the filter, you can find it in the AMCL pose topic. Yes? So here, if I do a ROS topic echo of the pose, you will see a covariance, which represents the error in the localization. Yes? Then, after the robot has performed this square movement, it has to print the covariance of the filter particles into the screen. Yes? Then you have to test that your code works. that you can launch this square move script, and your robot moves performing a square, and when it finishes, it brings into the screen the covariance. Okay? Then, when you know that this works, you will need to modify your program in order to do the following. So first of all, it will call the service in order to disperse the particles all around the environment. So first of all, you will call the global localization service. Yes? The service here. First of all, you will call the service in order to disperse the particles all around the environment. Then next, when the particles are randomly dispersed, it will perform the square movement. And when it finishes with the movement, it will check the particles' covariance. Then, depending on this value, if the covariance is less than 0.65, this will mean that the robot has localized itself correctly. So this is let's say, an acceptable error. Okay? Then, if this is the case, the program will end. If the covariance is greater than 0.65, it will repeat the whole process. So it will disperse the particles, it will perform the square movement, and it will check again the covariance. Yes? So this is the logic that your script has to do. Alright? Here you have some notes as well in order to complete this exercise, how to read this covariance matrix, and you should read always these notes, these data sections, because they will help you in order to complete the exercise. Okay? And yeah, that's all. We have finished with localization. So I hope you have enjoyed this chapter, and see you in the next one, which is path planning. Goodbye.